Alrighty. Good morning, everybody. Welcome back to Calc 3. Plan for today is we are going to finish Standard 5. Start off by kind of talking more about determinants, which we've talked about before, but I want to do a little bit more with them today, including talking about a cheeky method to make finding them a little bit easier. And after that, we're going to start Standard 6, which is going to be Unit 2 for the class, and start talking about multivariable functions. Got my usual office hours today at 2 o'clock, tomorrow morning at 10, tomorrow afternoon at 1. Don't be shy about signing up for an office hour appointment or asking for a retest. As far as homework goes, the Standard 5 quiz will be on Friday. And as a reminder, the first exam will be on Monday, and we'll only cover standards 1 through 5. Anybody have any questions or comments before we get started for today? Why are calendars always so nervous? They're nervous because they know their days are numbered. Okay, first of all, got some quizzes to pass by. We'll go ahead and do that. Katie. Avery. Lindsay. Sarah. Hannah. John. Gary. Luke. Dog. Whit. Emily. Jack McCoy. Benu. Will. Lori. Jacob. Jackson. Holly. Anna. And just as a reminder, I have been posting solutions for all the in-class quizzes, the version A's, on Blackboard. So for any of the in-class versions of the quiz you've taken, you can go on Blackboard and see how I did a particular problem. For anything that you did as a retest, I do not have solutions posted, but I would be happy to talk about it if you have any questions. Okay, so determinants. We've talked about determinants before in the context of Standard 3, looking at how we can use 3x3 determinants to evaluate a cross product. So I thought we would just start off by kind of reviewing what our procedure was for how to actually evaluate one of these determinants. So anybody remind me, what was the basic procedure we went through for how we would go about evaluating a 3x3 determinant like this? In particular, we had to do something special with sort of the top row of this matrix. What was that? Alan?
Multiply the top row by each of the 2x2 matrix of the numbers that are not in its row or column.
Yeah, exactly. We go along the top row and split this up into 3 separate 2x2 determinants, where each of the 2x2 is going to be made up of what's left if we were to remove the row and column with, say, 1 in it, for instance, which would give us 0, -1, 2, 1, if we remove top row, left column, minus 2 times determinant of what we get if we remove top row, middle column, so 3, -1, 4, 1, minus 0 times determinant of, it doesn't matter because we're multiplying it by 0, and then to evaluate the 2 by 2 determinant, we just have to kind of go down the main diagonal and multiply to get 0 times 1 is 0, minus 2 times 1 is -2. So we end up with 0 minus -2, so a positive 2. And 3 times 1 is 3 minus 4 times -1. 3 minus a -4 is 7. And we end up with 2 minus 14, or -12. And we use this 3 by 3 determinant process to talk about how to evaluate cross products, where the top row of your determinant matrix becomes just the standard basis vectors, I, J, and K, and your other 2 rows are the 2 vectors you were taking cross products of. So today, I want to talk about how we can go even further beyond plus ultra, and take 4 by 4, 5 by 5, etc., even higher level determinants. So let's take a look at that. And the determinant I want to look at in particular is going to be 1, 3, 0, 2, 2, 6, 0, -1, 4, 0, 0, 1, 0, 1, 1, 0. In general, the procedure you use to evaluate a 4 by 4 determinant works basically the same way that we would do a 3 by 3 determinant. You could just sort of work your way along the top row, alternating between positive and negative, and take positive 1 times the 3 by 3 determinant we would get if we removed the top row, left column. So it'll be 6, 0, -1, 0, 0, 1, 1, 1, 0, minus 3, going along the top row, times the determinant of what's left if we remove top row, second column. So minus 3 times the determinant of 2, 0, -1, 4, 0, 1, and 0, 1, 0, plus 0 times the determinant of what we get if we removed top row, third column. 2, 6, -1. Why am I bothering to write this down when I'm multiplying it by 0? And finally, we subtract, because we're alternating positive, negative, positive, negative. We're going to subtract 2 times the determinant of what's left if we remove top row, right column. 2, 6, 0, 4, 0, 0, 4, 0, 0, 0, 1, 1. We're basically just working our way along top row, plus, minus, and then using the same way, the same procedure we used to break up a 3 by 3 determinant into 2 by 2 determinants, we can break up a 4 by 4 determinant into the sum of a bunch of 3 by 3 determinants. Which fortunately, we don't need to evaluate that one because it's getting multiplied by 0. But if we took the other 3, what we would end up with is going to be, let's see, 6. The first one, we're multiplying by 1. That's going to give us 6 times the determinant of 0, 1, 1, 0, minus 0 times, who cares, minus, or plus, a -1 times the determinant of 0, 0, 1, 1, minus 3 times the expression 2 times determinant of 0, 1, 1, 0, minus 0 times cares again. And again, plus a negative 1 times the determinant of this time 4, 0, 0, 1. And then finally, our last determinant.
I just noticed on the note sheet,
there's a plus where I say there's a minus.
Is that?
That is a typo in the note sheet. That should be a minus. I was actually planning on addressing that after this example. But yeah, if you look up at the general formula for determinant of A, up at the top of the note sheet, it is minus A12 times blah, plus A22 times blah, minus A32 times blah, plus A42 times blah. Oh, oops, sorry. Strike what I just said. I'm on the wrong page. A11 times blah minus A12 times blah plus A13 times blah. It should then say minus A14 times that 3 by 3 determinant. Sorry, I realized that after I printed it out, but in my last class that it should be a plus minus and not plus minus plus plus. Yeah, good catch. Just finished evaluating this one though. We'll get a minus 2 times 2 times the determinant of 0, 0, 1, 1. Minus 6 times the determinant of 4, 0, 0, 1. And then plus some zeros. And if we simplify, we're going to get 6 times the expression 0 minus 1 is a negative 1. Actually, no, it's just this we're multiplying by 6. So we get 6 times negative 1 minus 0. Because 0 times 1 minus 0 times 1 is just going to come out to 0. So this top line just comes out to a negative 6. In the second line, we're going to have a minus 3 times the expression 0 minus 1 is negative 1 times 2 is negative 2. 4 minus 0 is 0, so we'll have a negative 2 minus 4, which when we evaluate will come to negative 3 times a negative 6, becomes a plus 18. And finally, this last line becomes minus 2 times the expression 2 times 0 minus 0 is just going to be 0, minus 6 times the expression 4 minus 0. So minus 6 times that becomes a minus 24. And then negative 2 times a negative 24 becomes a positive 48. Negative 6 plus 18 is positive 12 plus 48. It's going to give us a positive 60 for our determinant. I apologize for working through this one without consulting any of you, but once we got past this point, it's just a lot of tedious plug-in chuck. Keyword on tedious. These 4x4 determinants are kind of nasty. What's nastier would be if I were to give you a 5x5 determinant, which would involve splitting it up into 5 4x4s, which would involve splitting it up into 20 3x3s, which involves splitting it up into 60 2x2 matrices. It's not fun. Sarah, does that sound? Sarah, it looks like you're not enjoying that thought.
It's not something.
It does not. It is not appealing. But I wanted to do this process the long way so that you can kind of appreciate the cheeky shortcut method we're going to talk about next. Yeah, Paul?
You can choose any row or column to do the determinant. You can choose one that has the most zeros to do the
And that is indeed the shortcut method I'm finding you talking about. Yeah. Yeah, good call. That's going to, I'll address that in just a second. But first of all, just to talk briefly about the procedure we did at the start, we broke up our 4x4 into 3x3s by using the same procedure we did for 3x3 matrices. You just kind of worked your way along the top row and take each entry in the top row times the determinant of what's left if you remove that row and column. So for 1, if we remove top row, left column, we get 6, 0, negative. We get this bottom right corner of the matrix. We then alternate plus, minus, plus, minus. So we take minus 3 times the determinant of what's left if we remove top row, second column. That gave us the 2, 0, negative 1, 4, 0, 1, 0, 1, 0. And then we just keep working our way down the line like that. There is a method that makes taking this easier. And what that method involves, Holly, as I think you were alluding to, involves the fact that we went through this process of kind of going down the top row and taking element in top row times determinant of what's left if we remove that row and column. This process, by the way, is called cofactor expansion. Along the top, first row. But it turns out you don't need to do this along the first row of your matrix. We could do this instead by traveling down a different row of the matrix or a column of the matrix. So let's see what that. So Dr. Durso, what do you mean by that? Let's take a look. So I'm just going to write down equals 60 is kind of what we discovered, because I want to refer to that back. I want to refer back to that number later. So here's how sort of the easier method works. How it's going to work is take a look at your matrix to start off. Try and pick a row or column of your matrix that has a bunch of zeros in it. Does anybody see a row or column that has what looks like a lot of zeros in it in the original matrix? Yeah. Column 3. You say there's a couple rows. There's a couple rows of 2 zeros in it, but I like column 3 the best because it has 3 zeros in it. And what we're going to do is we're going to do cofactor expansion along that row or column that has a bunch of zeros in it. So in this case, we'll do it down the third column. And we can do this along any row or column, but it's going to be advantageous, as you'll see, to pick a row or a column that has a bunch of zeros in it, because it'll make our lives easier down the line. And what we're going to do is we're going to go do the same procedure where we take 0 times a 3 by 3 determinant minus 0 times a 3 by 3 determinant plus 0 times a 3 by 3 determinant minus 1 times a 3 by 3 determinant. We're going to do the same procedure we did along the top row going down the column, where the 3 by 3 determinant each time is still going to be the whatever's left in the matrix if we remove the row and column with that corresponding term in it. So in this case, I'm going to write this out again. 1, 3, 0, 2, 3, 6, 1, 4, 0, 0, 1, 0, 1, 1, 0. And we're going down column 3. There's a trick to this method, and that just like with the original determinant method, you have to alternate signs and go plus, minus, or potentially we might have to go minus, plus instead. Sometimes you have to do plus, minus. Sometimes you get to do minus, plus. And so there's always a question starting off of, are we going to start with a plus or with a minus? In this case, it doesn't matter because we're going to be multiplying by 0. But it will affect whether we're taking plus 1 times something or minus 1 times something once we get to the bottom of the column. And so the trick for determining, do we start with a plus and then alternate, or do we start with a minus and then alternate, is to take take the first element, in this case in the column, which is going to be the element in row 1, column 3, and we're going to add together the row number and the column number of that entry, which will be 1 plus 3 equals 4. If this number is even, then that's going to tell us we go plus minus plus minus. If the row plus column number of the first term in that row or column, if row number plus column number is even, we go plus minus plus minus. If it's odd, we would go minus plus minus plus. So if we were starting by going down along the last column, for instance, this would be the A14 entry, 1 plus 4 equals 5, and we would go minus plus minus plus instead. It's a little bit weird how it works out. And the reason why, I don't want to get into too much detail, it involves a lot of sort of linear algebra. But the idea behind it, and this is another way you can think about, do you do plus minus or minus plus minus plus, is you can start by thinking of the top left corner as corresponding to a plus. And then you can sort of alternate plus minus minus, minus plus minus, plus minus plus as you work your way across the matrix. So just start with a plus, a minus, a plus, a minus, plus minus, and then just alternate every other term. Whichever terms have a plus on them, those, if you're going to use that row or column to evaluate your determinant, you start with plus and then go minus plus minus. But if you're in a row or a column like the second row, for instance, where it's a minus plus minus plus, you have to do that to all of your terms. So let's go through and evaluate with cofactor expansion along column 3 and see if we can discover why it's advantageous to pick a row or column with a lot of zeros in it. So starting off, we're going to get 0 times the determinant of what's left if we remove the row and the column with this term in it, which will be 2, 6, negative 1, 4, 0, 1, 0, 1, 0, minus 0 times the 3 by 3 determinant of what's left if we remove the second row in third column, the one where this 0 is located, which would give us 1, 3, 2, 4, 0, 1, 0, 1, 0, plus this third term in the column, which is a 0, times the 3 by 3 determinant of 1, 3, 2, 2, 6, negative 1, 0, 1, 0. And finally, minus 1 times the determinant of what we get if we remove third column, bottom row. So 1, 3, 2, 2, 6, negative 1, 4, 0, 1. So we just expanded along column 3 by doing the same procedure we did across the top row, going plus, alternating sign, plus minus, except this time we removed we removed and took different 3 by 3 determinants than we did the first time. So here's my question to you. Why would we want to go across the third column and do it like this instead of doing it across the top row? What becomes easier in this case?
You don't have to do those first 3 by 3 determinants.
Yeah, who cares what these come out to be? We're going to multiply them by 0. They're just going to vanish and go away. And so the reason why it's nice to be able to expand like this on a row or column with a bunch of zeros is because then you end up being able to skip finding a lot of the determinants. Because you just end up with nasty looking determinant, but we're multiplying it by 0. If we're multiplying it by 0, who cares? So that, whereas over here, we picked a row, the top row, that only had a single 0 term in it. And so we only ended up with a single 3 by 3 determinant that we didn't need to find. We had to evaluate 3 of these things instead of just having to evaluate a single one by picking a column where there's only one non-zero term. So let's evaluate this out and see what we get. I'm going to keep this original matrix up just so we can see. And actually, I just remembered I had it over there. So if we work this out, we're just going to need to evaluate -1 times the determinant of this matrix. 1, 3, 2, 2, 6, -1, 4, 0, 1. I did that right? Yep. I have a question for you. We can evaluate this 3 by 3 determinant the way we usually would, go along the top row, but we could also choose a different row or column for this 3 by 3 determinant. That could also maybe save us some work. So does anybody have a column or a row they would like to choose to work their way along, to evaluate just this 3 by 3 determinant? Jackson?
Row 3.
Why?
If you're to do column 2, it has a 0 first row. And if you're to do column 2, you have to multiply by 3 and 6.
Sounds reasonable to me. So Jackson's proposing we expand along row number 3. Because he saw, first of all, that there's a 0 in that row, and expanding along a row or column with zeros in it makes things easier. And he liked 4 and 1 better than 3 and 6. I like 3 and 6 better, but I just have a weird, creepy fascination for multiples of 3, so that's just me. Let's do it along the bottom row. Bottom row, is that going to be a plus minus plus or a minus plus minus?
Plus minus plus.
Why is that?
Because it's in row 3, column 1. So yeah, 1 and 3 is 4. Just
Yeah, this entry right here that we're starting with is in the 3rd row, column 1, and 3 plus 1 is even. So that's going to tell us we're going to do a plus minus plus here. By the way, if we'd gone down the second column, first row, we would have had to do a minus plus minus to make that work. But 3rd row, other way to think about it is if this is plus, then this is going to be minus, and this will be a plus. So we get a plus minus plus that way as well. And that's going to give us 4 times the determinant of what's left if we remove the row and the column with 4 in it. So 3, 2, 6, -1. Minus 0 times the determinant of, I don't really care, plus 1 times the determinant of what's left if we remove bottom row, rightmost column, 1, 3, 2, 6. And if we evaluate that out, we'll get -1 times 4 times -3 minus 12 is -15. And I'm not even going to give back the time of day. Plus 1 times 6 minus 6. Oh, well, that's just going to be 0. And so what this comes out to is going to be -1 times 4 times a -15. 4 times 15, negatives cancel out. Gadzooks. You got the same answer. If you remember, when we expanded along the top row, we ended up having to find 3 3 by 3 determinants, which ended up involving something like 9 2 by 2 determinants. Here, we only needed to find two 2x2 determinants. But we arrived at the exact same answer. And the moral of the story is, it doesn't matter which row or column you expand along. You should, assuming you do all your arithmetic correctly, you should get the same answer regardless. But if you expand along a row or a column with a lot of zeros in it, it can make your life much easier. Just because then you get to multiply things by 0 and you don't have to multiply, or you don't have to evaluate as many determinants in the end. That's why, Brianna, I like your choice of column 3, and that if you had chosen, say, row 3 instead, you would have had to do 2 3x3 determinants instead of just 1. What questions do you all have about this process?
So we got the new 3x3.
Yep, we got this one.
Yeah. So is that going to be plus minus plus as well, or is it going to be plus minus minus?
It's always going to alternate as you work your way across a row or column. So it's going to be plus minus plus.
Okay, so it doesn't matter that in the 4x4.
Ah. I gotcha. I see what you mean. Yeah, because the 401 was a plus minus plus in that 3x3, but here it was a plus minus, and that 1 was coming from here where it was a minus. That's a good question, Katie. But yes. It doesn't matter because once you get it down to a 3x3 like that, it doesn't matter where those terms were in the original matrix. But all that matters at this point is where they are in this 3x3 matrix. So the fact that this one actually was corresponding to a minus sign, if, say, we had tried to expand along row 3 or column 4 in the original matrix, that doesn't matter anymore. Good question. Glad you asked. Any other questions? Let's do one more just as practice. And I'll let you all decide where we expand along the way. By the way, you don't have to write out every time, expand along row 3, expand along column 2, or whatever. I did that for these kind of first examples just to make it clear what we're doing. But if you understand what you're doing, you don't need to write out which row or column you're expanding along each time, unless you want to. So let's do this top one on the second to last page. 1, 3, -4, 5, 0, 0, 2, 0, 0, 2, 4, 6, -1, 5, 7, 2. I would like to evaluate this determinant. Does anybody have a row or column they'd like to propose for where to expand along? Jerry?
Row 2.
Why row 2?
There's 3 zeros.
3 zeros. I like the sound of that. Yeah, this row has a bunch of zeros in it. So expanding along that row sounds like it's going to involve only finding a single 3x3 determinant. Whereas if we'd done the top row, it would have been 4 3x3 determinants. For expanding along row 2, are we going to have a plus minus thing going on, or a minus plus minus plus?
It could be plus minus since it's an odd number.
It's going to be plus minus since it's an odd number?
No, sorry, it would be minus plus because it's a even number of commas, so it would be minus plus.
Yeah. So if you look at this first entry in the second row, it's in the first, sorry, not 81. Yeah, it's in the second row, first column. Row plus column number is odd, therefore we start with minus, and it becomes a minus plus minus plus. All that really matters is telling us whether we're having plus 2 times something or minus 2 times something, because the 0 terms, the minus and plus, don't really matter. Other way to check, put a plus in your top left corner, alternate down, This has a minus on it. And so we'll get negative 0 times something, plus 0 times something, minus 2 times the determinant of what's left if we remove the row and column with that 2 in it, which is 1, 3, 5, 0, 2, 6, negative 1, 5, 2, and then plus 0 times another 3 by 3. I'm not bothering to write out these other 3 by 3 determinants because they don't matter. And just in the interest of trying to be efficient with time and space. After all, we don't want to upset the space-time continuum. We end up needing to evaluate negative 2 times a 3 by 3 determinant. Anybody have a candidate for a row or column they want to expand along here?
Row 2, it's got the 0.
Yeah, just do row 2 again. Has as many zeros as any other row or column. I would propose row 2 or column 1. Jackson, I think, is twitching over there that we chose row 2 when it has 2 and 6 instead of just 1 and negative 1. But it ends up being the same number of determinants either way. So if we expand on row 2, minus plus minus, plus minus plus. And why is that? Actually, by the exact same reasoning as with the 4 by 4. It's second row, first column, comes out to it. Row plus column is odd, therefore we start with the minus. Or plus minus plus, minus plus minus, plus minus plus. We see minus plus minus that way too. So we're going to get negative 2 times 0 times who cares, plus 2 times the determinant of what's left if we remove row 2 and column 2, so the outer corners, 1, 5, negative 1, 2, minus 6 times the determinant of 1, 3, negative 1, 5, and if we evaluate that out, what we're going to get is negative 2 times 2 times this determinant, which is 2 minus a negative 5, which is 2 plus 5 is 7, minus 6 times 5 minus a negative 3, which is 8. And we're going to get negative, negative 2 times 14 minus 48, which is negative 2 times negative 34. And our final answer will be a positive 16.8. Dr. Gersel, are we going to have to do this on a quiz or test? You better believe it. But if I give you a 4 by 4 or higher on a quiz or test, I'm likely to make it one with lots of zeros in it, or at least one row or column with a lot of zeros in it to allow you to skip some steps as long as you know what you're doing. And I'll be nice with, since there's plenty of opportunity for arithmetic errors on stuff like this, when I'm grading, I'll be nice with regards to, oh, you forgot a minus sign. Oh, you said 2 times 7 is 16 and not 14. And I don't really care about that. As long as it's clear you understand how the process works. Any last questions or comments about determinants? Dr. Gerstel, why are we doing this? Looking at 4 by 4 and higher determinants isn't as necessarily helpful for doing things like cross products, But later on down the line, when we look at actually some theorems like the second derivative test, if you recall, the second derivative test in Calc 1 says something like, oh, if you have a critical point where your function is concave up, where the second derivative is positive, then it's a minimum. If it's concave down, then it's a maximum. What we're going to be seeing in a few standards from now is if we try to do the same test, we end up having to see whether a certain 4x4 determinant comes out to positive or negative. Tell us whether we end up having maxes or mins in looking at our functions. So this is going to be a helpful process for us to be able to do going down. There's a couple extra a couple problems at the end of the packet we didn't do. I encourage you to try those out as just get yourself some extra practice, a little bit of extra practice. And with that, you're finally ready. Start doing some calculus. This, by the way, was the cutoff point for the exam. This next standard will not be on exam 1, unless you all really want, unless you all ask for it. I can maybe be, watch where I'm going. I can maybe be convinced. Because this is going to be kind of a turning point in the semester for us. Everything that we've done up till this point, I would argue, is sort of the pre-calculus equivalent of multivariable functions. And that we learned kind of how to do basic algebra involving things like vectors and matrices and a few of the applications of these sorts of ideas. But from here on out, we're going to be taught, this class is going to feel, I think, a lot more like a Calc 1 class. And that in the next unit, we're going to be looking at things like functions and limits and continuity and derivatives and optimization, finding maxes and mins. But we're going to be looking at functions involving vectors instead of functions from Calc 1 and Calc 2, which just involve scalar values. So to start off, just a little bit of a thought exercise. What's the first thing that comes to your mind when you think about functions in a math class? In other words, based on your past experiences in math, what do you think of when you think of functions? Now, inputs and outputs. Something with an input and something with an output. What else comes to mind? In terms of maybe function, what they are, or what are things that you do with functions?
Graphing them.
Yeah, things that you can graph. For instance, in most calc classes, you write y as a function of x, so that if you see something like y equals x squared, or f of x equals x squared, which takes in an input x and spits out x squared as an output, we can graph that by saying for every x coordinate, we're going to let y be equal to the corresponding output of the function when that x coordinate is put in. So f of x equals x squared looks like this, where we have points along the x-axis that are our inputs, and our y values correspond to the outputs.
Sorry, I'm just cracking my wrist.
Oh, okay. Looked like you had something, and then your hands started going in circles, and I started to get dizzy. Anything else that comes to mind when you think of functions? Why do we care about functions? Other than, ooh, look at that graph, they're pretty.
They can be good models for like, real problems.
Yeah, functions can be used to model real-world problems. Absolutely. Problems like I'm working at a company and I want to optimize and I want to maximize my profit often comes down to here's a function. Make this function find the value of x that makes this function as big as you can, and that's going to be how you maximize profit. You have a function that sort of models a real-world problem, so to speak. Anything else? So I would say that all of these are definitely ideas we're going to be talking about in the next several standards in this class. And that our functions, just like in Calc 1, are going to have inputs and outputs to them. The key difference is our inputs are going to be, and outputs are going to be vectors instead of just scalar values. We're going to be doing some graphing, where in some cases, if I were to ask you, here's a function with a 5-dimensional input and a 10-dimensional output, you're probably not going to be trying to visualize that too much because human mind doesn't work that way. But we're going to be looking at some 3D graphs. We've already sort of seen a few on Plot 3D. We're going to be looking at plenty more. And in about five standards from now, we're going to be looking at several standards that are focused on sort of real-world problems in terms of how can we use these sort of calculusy tools we've been developing to actually do something that you might want to do if you're working for a company or trying to minimize your energy usage on your electric bill, or minimize your electric bill, or anything else that you might want to make big or small in the real world. So to start off, in Standard 6, we're going to be looking at kind of the basics of functions, talking about some terms you may have seen before. And I want to start off with talking about domain, range, and codomain of a function. So in our class, we're going to be talking about multivariable functions, which basically mean our functions are typically going to be involving vectors with multiple components to them. And in particular, we're going to just say that a function, by the way, if you ever see me write fxn, that means function. I'm just lazy to write out the whole word. A function, here, I'll be nice and write it out once, just to prove I can. A function is going to be a rule that takes vectors in some Rn, and it's going to spit out vectors in either the same Rn or a different Rm. And that's just going to be a rule of how to map vectors in Rn to vectors in Rm. This notation of Rn, arrow, Rm, we're going to use to mean we're starting in Rn. That's going to be where our inputs to the function live. And the outputs of the function are all going to live in Rm. And let's look at an example over to the side while we define a few terms. Let's say we have a function that's going to take in and spit out vectors in R2, where f of a vector x is going to be defined to be x divided by the magnitude of x. Or in other words, we're going to multiply x by the scalar value 1 over its own magnitude. We've seen this expression actually appear back towards the end of Standard 2, when we talked about given a vector x, multiplying that vector by the scalar 1 over the magnitude of x does something special to that vector. how can we sort of describe in words what does this function do to a vector x? Go here.
Well, it's the unit vector, so the vector of 1 to 1 pointing in the same direction.
Yeah, that's exactly it. We can describe f of x, the function f. What it's going to do is it's going to take in a vector x and it's going to spit out the unit vector, meaning vector of length 1, that's going to point in the same direction as x. So that's a function. It's going to be a function that takes in vectors, and it's going to spit out vectors each time. Let's just say a quick example, see how this function works. If we were to plug in, say, the vector in R2, 3, 4 into this function, what we would get is it's going to be 3, 4 times 1 divided by the magnitude of 3, 4. We're just swapping in anywhere we see a vector x symbol. We're going to swap in that vector x, which is 3, 4. What is the magnitude of 3, 4? We're the Pythagorean theorem it up. Up?
5.
I agree. Because this magnitude, don't forget, is just going to be 1 over square root of the component squared, sum of the components squared, which square root of 3 squared plus 4 squared is the square root of 9 plus 16, which is the square root of 25, which is 5. And if we multiply the vector 3, 4 by a fifth, we're going to get 3/5, 4/5 as our output. So in other words, what our function did was it took in the vector 1, 2, 3, 1, 2, 3, 4. If this was our vector v, then our vector f of v was going to look like this. It basically just took our vector and made it shorter so that the new vector pointed in the same direction, but also happened to have a length of 1 attached to it. And we're going to look at several other examples of vectors as time goes on. But I want to do 3 things with this function. I want to find the domain, I want to find the range, and I want to find the codomain. So starting off, the domain of a function is basically just the set of vectors that you can plug into the function, the set of all inputs that gives an output that makes sense. This is going to be the set of all inputs to the function f that give outputs that make sense. So for this particular example, if we were to evaluate what the domain is, we would have to see which vectors can we plug into this function and somehow not end up doing something terrible like taking the square root of a negative number, or dividing by 0, or trying to somehow break math. So let's ask this question. Are there any vectors in R2 that you would consider to be in the domain or not in the domain? How about, let's say, not in the domain? Yeah?
The 0 vector?
Why isn't the 0 vector in the domain?
Because the 0 vector has a magnitude of 0, and so then dividing by 0 would give you like a number that would exist?
It would give you sadness.
Yes.
Yeah, if we try to plug the 0 vector in, the magnitude of the 0 vector is 0. 1 divided by 0, no bueno. Pro tip, don't divide by 0. To remind me, I can start class off next time with by proving that if it's okay to divide by 0, then you can prove only one number exists. And you don't want that. So the 0 vector's out, not in the domain. Are there any other vectors that in R2 that we are not allowed to plug into this function? Or is everything else okay? Like that any vector other than just strictly the 0 vector, we can plug in and get an output that makes sense. Sarah, I see a thumbs up. I agree. I think everything else in R2 except for the 0 vector is going to be okay. Because any other vector we try to plug in, as long as it's not just 0, 0, it's going to have a magnitude that's positive. And 1 over a positive number, yeah, that's something you can always do. And multiply any vector by a positive scalar value, yeah, that's something you can always do. So the only vector that's not in the domain is the 0 vector. And here is how I'm going to write out the domain. First of all, if you ever see dom of f, that just means the domain of the function f. It's going to be a set of vectors. It's going to be a set of inputs that's okay to plug in. Here's how I'm going to write it. I'm going to write it as the set of all xy in R2 colon xy is not equal to 0, 0. If you haven't seen this notation before, it's called set builder notation. Here, I'll rewrite it up here since some of you seem to have both seen it. And just to give you a sense of what this means, get two ready to go. We still have 10 minutes almost. These symbols are set brackets. So the fact that I put like this curly bracket here and here just means we're looking at a set of things. Like a set of vectors, it does something, a collection of vectors. XY in R2 basically telling us what are the vectors that we're allowed to have. So we're allowed to have our domain as a set of vectors in R2. And then the colon, xy is not equal to 0, 0, just means we're setting a condition on which vectors in R2 we're allowed to have. And since the domain is a set of things we can plug into the function, we're excluding 0, 0 as a candidate from this set. This is going to be a condition on the vectors in the set. So that's what the domain is. It's just what things can you plug into your function and get an output that makes sense. In this case, our inputs are just any vector in R2 other than the 0 vector. Any questions or comments so far? By the way, we could theoretically try and plug in vectors in R3 or R4 or higher into this function. It's defined in pretty much the same way. Here, though, we specified at the start that we're only considering vectors in R2 to begin with. So that's why I said vectors in R2 instead of R2 and R3, for instance. Next one is going to be codomain. And this is probably the one I feel you're probably least likely to have seen before. The codomain is just going to be the set in which all your outputs live. The set of all vectors where the outputs live. And typically, at least in this class, it's just going to be Rn. The Rn where all your outputs live. And so for this particular function, what can we say that the codomain is. In other words, what's the Rn where all of the outputs to our function are going to live? Molly? Yeah, just going to be R2. If you ever see this sort of notation for your function, that right there, the one after the arrow, is going to be your codomain. All of the outputs for this function live in R2. That's the codomain. Depending on your function, the codomain may be a different set entirely. And finally, I want to talk about the range of a function f. The range, usually the trickiest to find. The range is going to be the set of it's just going to be the set of vectors that are outputs to the function. Not just the set where the outputs live, but the set specifically of the outputs themselves. So the range of your function is the set of all vectors in the codomain in Rm that actually get mapped to by some vector in the domain. It's the set of all outputs to your function, not including things that have no input mapping to it. So for this case, let's start by just looking at two vectors individually. Which of these vectors is going to be in the range of the function f here? In other words, which of these two vectors is going to have something that maps to it? What? Why? Yeah, we could say that 0, 0 is going to not be in the range of f, since no vector maps to it. There is no vector in R2 that you can say, if I were to take a vector of length 1 pointing in the same direction as the original vector, I would get 0, 0. It's never going to happen. 0, 0 doesn't have the right length. But 1, 0 is going to be in the range, since we can find some values that will map to it. Can anybody give me a vector in R2 that if we were to plug that vector into the function f, we would get 1, 0 as an output? In other words, I'm looking for a vector that's going to happen to map to 1, 0.
5, 0.
Sure, 5, 0. 5, 0 points in the same direction as 1, 0. They're both pointing to the right, and if you were to graph them out. But 1, 0 is of unit length that has length 1 pointing in the same direction as 5, 0. So yeah, I would agree. So 1, 0 has at least one vector mapping to it, therefore it is going to be in the range. What would be some other vector that maps to 1, 0? Yeah, any positive number for x, 0 for y would work. You could say it's equal to f of pi comma 0. You could say it's equal to f of itself. 1, 0 maps to 1, 0. Since 1, 0 is a unit vector pointing in the same direction as 1, 0. So 1, 0 has lots of things mapping to it, which is totally fine. It just needs one thing mapping to it to put it in the range. And now, let's see if we can write out the entire range as a set of vectors. So what can we describe as how can we describe the set of every single vector in R2 that happens to be in the range, that gets hit by something? How can we characterize all of those vectors?
This is going to be xy vectors in R2, like colon condition with the magnitude of x, comma, y equal to 1.
Like that? I like it. Yeah, nice job. It's the set of all vectors whose length is 1. Same startup, we have these set brackets to say we're looking at a set, a collection of vectors. Vectors in R2 specifically, with the condition that their length has to be 1. Because if their length is 1, then they're always just going to be equal to f of themselves, for instance. But if their length is not 1, they're not going to be in the range because every element in the range has to be a unit vector since f only spits out unit vectors. All right, now we are, oops, sorry, only a couple minutes over. We're out of time for today. When we come back on Friday after the quiz, we're going to talk more about domain, codomain, and range. And we're also going to take our first steps at looking at how do you actually graph some of these multivariable functions. We'll be pulling top plot 3D back up. Hope you all have a good rest of your day. I'll see you all on Friday.